Connection design example 1. Let's consider in this example, design a lap joint to connect two plates 100 mm by 8 mm and 100 mm by 10 mm plates. These are subjected to 90 kilonewtons. Use Fe 410 grade steel for plates and bolt grade is 4.6 of M16 mm bolts are used. Now, generally we discussed the generic capacities for the connection we are testing is shear strength of the bolt, bearing capacity and tension rupture of the plate, tension capacity of the plate. Generally the rupture is the governing case. So first let's see the design data. So what are the data we need actually? First thing is bolt dia equal to 16 mm. So bolt hole dia equal to 16 mm plus 2, which is 18 mm. So when you do the net area of the plate, we need to deduct this hole and this hole, which is actually 18 mm. But when you do the bolt diameter area, you have to consider this one. Okay, we have discussed that one. Now bolt for grade of 4.6, the FUB is equal to ultimate strength of the bolt, which is 400 Newton per mm square. So similarly, the FU of the plate, you can simply make it as FU or FUP also can be used just for a naming. For the plate, FU value is 410 Newton per mm square. Now we need to calculate the shear strength of the bolt. What is the equation of the shear strength? Shear strength VNSB equal to FUB by square root of 3 NN ANB plus NS ASB. So we discussed NN equal to number of shear planes at threaded portion. For example, if you can see here, this up to from here is a threaded portion. From here to here is non-threaded portion, shank area. Shank area, this is a threaded area. So now we have to see exactly where the bolt going to be failure for shear. So this is a 10 mm thickness failed at the threaded portion, then we have to take the net area of the bolt. If it is failing over this portion, we have to take the gross area of the bolt. But how do we know that this bolt is going to be failed in gross area or the net area? So it is a bit difficult during the example, but in real-time projects, we have to consider the bolt length, and then we need to find out the shank, this length and this length and the connecting elements, and then only we can able to find out whether this bolt is going to be failed over here or over here. But in order to understand this example, we can assume that because the bottommost plate is 10 mm thickness, it is going to be failed in the threaded portion. So that means number of shear plane at threaded portion is going to be 1, and A and B is actually net area of the bolt we need to consider. The shank area is actually, there is not going to be any failure. So this NS equal to 0 and ASB is anyway is the gross area of the bolt. So now let's consider here what is the A and B. ASB equal to pi d square by 4. D equal to diameter of the bolt, which is, this is the D. So is equal to pi 16 square by 4. equal to 201.6 mm square. So A and B equal to, we calculated 0.78 times of pi d square by 4, which is also equal to 0.78 times pi 16 square by 4, which is going to be a 156.8 mm square. So now we will go and calculate the shear strength of each bolt. VNSB equal to FUB equal to 400 by square root of 3, number of shear planes at threaded portion equal to 1 times A and B equal to 156.8 plus number of shear planes at shank area equal to 0, ASB equal to 201.6. So now this comes around 36,217.9 newtons. You can consider this one as 36.217 kilonewton of the force. So now design strength of the bolt equal to design strength of the bolt equal to VDSB equal to VNSB by lambda MB. Partial safety factor need to be multiplied. That means 36.217 divided by 1.25 is the partial safety factor, which is equal to 28.974 kilonewtons. So this is actually a shear strength of the single bolt. If we have a multiple bolts, we need to multiply this into the number of bolts so that you can get the total shear strength of the bolt within that connection. Let's discuss about bearing capacity. The bearing capacity of the bolt is nothing but when the plates are subjected to the force, the bolts are in shear. And when the bolts are subjected to the shear, if there is no significant enough friction in the joint to prevent the slip, the bearing will occur. Around the bolt, the deformations will be occur. So this is called actually a bearing type connection, and we need to design for the bolt the capacity of the bearing capacity to resist the external loads. So what is the equation for bearing capacity? So VNPD equal to 2.5 times KB DTFU value. So whereas the KB is actually a factor, it depends upon the minimum edge distance, pitch distance of the bolt. D equal to diameter of the bolt, T equal to thickness of the plate, and Fu equal to the minimum ultimate strength of the plate or bolt, whichever is going to be failed. So the bolt also may subjected to the bearing and plate also will be subjected to the bearing. So let's find out the minimum design parameters which is required for bearing capacity calculations. The minimum pitch distance equal to, which is equal to P equal to 2.5 times D, which is equal to 2.5 times 16 equal to diameter of the bolt, which is equal to 40 mm, and minimum edge distance. Edge distance E equal to 1.5 times bolt hole diameter, which is equal to 1.5 times 18 is the bolt hole diameter, not 16, okay, which is equal to 27 mm. So we cannot exactly provide 27 mm, so we can round it as a 30 mm. So let's provide for our connection P equal to 40 mm and edge distance equal to 30 mm. So now KB equal to, we already discussed, which is minimum of E by 3DO or P by 3DO minus 0.25 or FUP by FU or 1.0, whichever is minimum. So let's calculate this value. Minimum of 30 by 3 times 18, DO equal to diameter, hole diameter, right? And 40, which is pitch distance, divided by 3 times 18 minus 0.25, comma, FUB equal to bolt ultimate strength is 400 by plate ultimate strength is 410, comma, 1.0. So now let's summarize these values. You will get minimum of 0.555, 0.4907, 0.9756, comma, 1.0. So which is, what is the minimum value over here? 0.4907. So now let's find out the nominal bearing strength of the bolt. Nominal bearing strength of the bolt. So the thickness, what we need to consider, we have a two plates. So the plate 1 is actually a 8 mm and the connecting plate is actually a 10 mm plate. So let's consider the minimum plate always gives the lowest capacity. So we need to find out the minimum capacity when we are designing actually, right? So let's consider the minimum plate thickness. Plate thick, T equal to 8 mm and FU equal to 400 Newton per mm square, which is actually bolt FU value, which is minimum one. Now the equation VNPD equal to 2.5 times KB dt and FU, which is equal to 2.5 times 0.4907 times 16 times 8 is the thickness of the plate and 400 is the FU value, which comes around 62,809.6 newtons, which can convert it into kilonewtons by 1000, which is equal to 62.809 kilonewton. This is the capacity of one bolt. If you have a number of bolts, we need to multiply each one. So our capacity of the connection is 90 kilonewtons. If one bolt is actually 62, at least we need to provide 2 bolts in order to take care of the bearing strength. Okay. Let's discuss right now design bearing strength. The design bearing strength equal to, which is actually VD PD equal to VN PD by lambda MP, which is equal to 62.809 divided by 1.25. This comes around 50.24 kilonewtons is the design bearing strength. So this is, we call it as a 2. So now what is the design strength of M16 bolt? The design strength of M16 bolt equal to the minimum of shear. If you consider this one, the minimum of, this is 1, the minimum of shear strength of the bolt, and subjected to 90 kilonewtons. 90 kilonewtons is the force, and this need to be multiplied by 1.5 to get the factored force, and this is actually shear strength of the bolt. Now let's go to the 1 and 2. So that means minimum of 28.97 or 50.24, which is actually 28.97 kilonewtons. What is the force we have? Equal to 90 kilonewtons, and if you multiply it by 1.5 as a factored load, then it comes around 90 into 1.5, which is actually 135 kilonewtons. So now let's make it the number of bolts is required for this particular connection. Number of bolts required equal to 135 kilonewtons by 28.97 equal 4.65 bolts is required. So you can provide actually, we cannot provide actually 4.6, and even if you make it as a 2 number of bolts in each row, it may comes around 2 bolts each row. Okay, now we find out there is a 6 number of bolts we are going to provide for this particular connection, 2 bolts at each row. So this is 1 bolt and this is 1 bolt at each row. Okay, so now we need to find out the member tension, rupture or yield capacity, which is going to be a predominant over here. So we already discussed that the tension TDN, the check plate strength plate strength TDN equal to 0.9 times AN FU of the and lambda ML. So now the FU equal to the plate yield strength and AN equal to net section area of the cross section. For example, if you take at this portion 1 to 1, the AN equal to B minus number of bolt into bolt hole diameter times thickness of the plate. So the bolt diameter is 16 and bolt hole diameter equal to 18 mm. So that means B equal to 100 minus 2 times 2 number of bolts equal to 2 in a cross section, which is actually 18 times the thickness of the plate. We have 2 plates. One is actually 8 mm plate, another one is the 10 mm plate. We need to take the lowest thickness of the plate because that is the one is going to be failed first. So to take 8 mm. So which is equal to 512 mm square. Now TDN equal to 0.9 into 512 into 410 divided by lambda ml equal to 1.25, which is equal to 151.14 kilonewtons, which is greater than 135 kilonewton of the factored force. So the connection is okay. So that's all. So first, actually what we have done over here, we find out the shear strength of the bolt and we find out the bearing strength of the bolt. We took whichever is the minimum, and then based on that we applied the total factor force divided by the bolt capacity. So we will get the number of bolts. Once we get the number of bolts, we design for the connection. Once this connection has been designed, then we identified the plate capacity, plate tensile capacity. If that capacity is greater than the factored load, then our connection is safe. So this is the way we can design for the any type of the